Again, thank you for joining me. Thanks for taking time out of your day to learn about distributions in at-risk. It's one of the most popular questions that I get after I do any of my introduction to at-risk webinars is how do I know what distribution to use? So hopefully by today you will have just a better idea or a little bit more confidence in which distribution to choose. And please know that don't sweat it. Don't sweat it too much. I always start my introduction to at-risk webinars with this little slideshow. And it's just, I want to just repeat the slideshow without even showing the slideshow with you, but I want to repeat it because my guess is a lot of people that are watching this presentation have already seen the intro to at-risk or intro to risk analysis using at-risk webinar. The first part of it is, if I put my foot in boiling water and I put my foot in ice, am I comfortable? If I go target shooting with a friend and my friend hits 2 feet to the left of the target, I hit 2 feet to the right of the target, on average, did we hit the target? If I start my day with a beautiful sunrise and it ends in a tornado, on average, did I have a good day? Obviously, the answer to all of those questions are no. So that just shows you that sometimes the average isn't the way to go. And that is why we do Monte Carlo simulation. And that is why we choose distributions so that we can simulate off those distributions and then have a bigger picture at the end of it. So with that being said, know that whatever distribution you choose is going to be better than just going with a single point estimate, like the single point estimate of saying on average we had a good day. Okay, so just start that off with just some mental notes on that. Okay, so we're going to go ahead and get started here. First thing we'll say is that our objectives for today are going to be questions to ask when you're choosing your distribution. Do you have data and can it be used? Or should it be used? What do we know about the input? That's another key question. So that's going to be a little bit more of a pragmatic approach, and we'll go through that. I'm going to show you some distribution fitting for when you have examples, and I'm also going to show you some model examples so that we can show how we can take that pragmatic approach to it. And then I'll also just mention a few additional things for us to consider. This quote from Donald Rumsfeld, I think, is just perfect for what we do with at-risk and with Monte Carlo simulation. And for anyone that attended our user conference in Nashville last week, our keynote speaker actually also brought up this quote, and I was like, that's awesome. It's awesome that not only he uses the quote, but also I use it on a regular basis for the webinars. But there are known knowns. These are things that we know that we know. There are known unknowns. That is to say, there are things that we know we don't know. But there are also unknown unknowns. There are things that we don't know that we don't know. And the known knowns are those known inputs, those set values that we have control over. The known unknowns is what we're talking about today. We're talking about our inputs that we're going to use in order to model our situation and draw a simulation on our model. And then that is going to be able to determine this output, this complete output. So today is going to be all about those known unknowns. And what do we know about those unknowns? And that's going to be super important. So the 6 steps in doing risk analysis, I do these and I cover these in almost every single webinar I do. Explore the model logic, making sure you truly understand where your values are coming from in your spreadsheet. Super important. Use the trace dependence, use the trace precedence. You're in Excel. Our product at-risk is an add-in to Excel. So make sure that you really understand that model logic right from the get-go. Then we're going to talk, the next step is designated inputs, and that's what today is about, right? Today is about discussing our inputs and how do we know what inputs to designate, and also how do we designate them? Designating our outputs, letting at-risk know which output we're most interested in learning more about. Simulating, it kind of goes without saying, it's the easiest actual part of the entire process because all we have to do is let at-risk know how many iterations, how many simulations to run. And then analyzing the results. That is why we do Monte Carlo simulations, so we can analyze the results and then communicate them to others. The key factor here is communicate at the end. Is at the end of this list, but it is actually at every single step in this process. And it's important to realize that it is important to include others in the process of risk analysis, because it may be subject matter experts, it may be someone that has previous experience with the situation, it may be someone that set up the original model. So you want to make sure that you're in communication with others involved in the project itself. When we talk about distributions, and for those that are just browsing, what we do typically is we have input distributions that represent the uncertainty in our data, and then we draw random values from those input distributions, run simulations, basically plug in random values into our spreadsheet based on those input distributions, and we then get a new distribution of outputs that are with our specific output variables that we're curious about. And I will show some simulations, but it'll be later on in the presentation. But why a distribution? Why do we need a distribution? A distribution describes a shape that represents your known unknown in a way that is so much easier to convey to others. So if I were to say, oh, it's a fatigue life function, you might not really be able to understand what that looks like, what it is. So it's a lot easier to show people a distribution, and they can visualize, because humans are visual animals, so they can visualize what this distribution looks like. And this is just a handful of some examples. So the one in the middle is the normal distribution. You're all pretty much familiar with it from your Stats 101 classes and Stats 102 classes from high school or college. And the reality is, not too often will you use the normal distribution in general practice with a lot of the different industries. There are specific situations that you will see the normal distribution, and typically it's going to be small changes or adding different distributions to one another, and we'll get into that. But just the normal distribution is the bell curve that people are most familiar with. But an example I like to give of this as to how could it accurately represent some of the items that are typically talked about is, oftentimes they'll say, oh, normal distribution, that's perfect for height and weight of people, right? Let's just take the weight one, for example. If the average American male weighs 190 pounds, we picture the average American male being somewhere in the middle of this distribution, right? Well, there's a good chance that there might be someone that weighs 380 pounds. So he's going to be on the tail end of this distribution, correct? Is there an equal chance of someone weighing, an American male weighing 0 pounds, as there is the chance of an American weighing 380 pounds? So do you see where I'm going with that? So sometimes there may be other distributions out there that will represent what you're trying to represent in a better way. Hence why we're attending this webinar. This distribution down here, the 0 and 1 distribution, it's a Bernoulli distribution. The parameter for it is simply the probability of there being a 1. So if we did 100 simulations, then out of the 100 simulations, if there's a 30% chance of there being a 1, then 30 out of those 100 times there would be a 1 showing up in your spreadsheet. The Bernoulli function is an on-off switch, a yes-no switch, true-false switch, anything of the sort. So we can actually use this to our advantage when we go through an example model where there's a chance that a competitor might enter the field. If a competitor might enter the field, we can plug in a Bernoulli function, and that Bernoulli function can represent the chance. So if there's a 30% chance, then only 30% of the time of our simulations will we actually put a 1 in that cell. That may trigger different values being populated throughout the cell, because we're in Excel. So the Bernoulli function is an on-off switch. Top left here, this is the Poisson distribution. Poisson distribution is similar in the sense that it's a discrete function. It doesn't have the smooth curve to it. It's either a 0, a 1, a 2, a 3, a 4, or 5, or in this case even a 6. similar to the way Bernoulli was a 0 or 1. In this situation, this represents the number of events that may take place over a certain amount of time. So maybe it's a 6-month stint, and during the 6-month stint, how many times are we going to have bad weather that shuts down our project? You can actually create a distribution that will trigger different possibilities for that. So maybe, it'll be 40% of the time a 0, and then maybe it's 50 or 60% of the time a 1, or I shouldn't say 40 and 50 and 60, but it would be 35% of the time maybe for 0, 40% of the time for 1, and then it goes down. So this will actually populate your spreadsheet with different values based on this Poisson distribution. Now we have the exponential function. A lot of people are pretty familiar with the exponential function, right? So the exponential function could represent the time in between the 0 and 1, or the 1 and 2, so that maybe the time in between the different events that occur in a Poisson distribution. So there are all different ways. In exponential function, you could probably come up with some other ones, and we'll cover some of those in general. Then, in addition to that, we could also have, this is that risk fatigue life. Risk fatigue life is actually a distribution that's used to model lifespan of light bulbs, or lifespan of certain products out there. So, a duration that then tapers off over time. Another distribution is the beta general, and I'll be honest with you, the beta general, depending on the different parameters that I use, is quite flexible. So when we do distribution fitting, oftentimes you might see beta general pretty high up on the list because beta general is a flexible function. And beta general in this situation, this particular situation, could represent something with epidemiology. The risk of flu for infants is really super duper duper high. And then the immunity systems are, the risk is a lot lower for middle-aged folks. And then maybe end of the lifetime, there's this spike because elderly are super susceptible to flu. So now all of a sudden this picture can really represent a whole lot more than the math that would be behind this, the alpha 1, alpha 2. That isn't going to help people to visualize what this represents, especially when you're talking to non-statisticians. And that's typically who we are communicating with after we do our analyses. So it's important to also take that into account, is who are we going to be communicating with. I also saw that, maybe this represents marriage, the happiness in marriage. You first get married, you're super high on life, and then the honeymoon's over, and then you have life hit. And maybe you have kids, and maybe you're building houses, and maybe you're changing jobs, and maybe you're moving, maybe you get laid off. And then when you retire and you're hanging out with your loved one at the end of life, maybe your happiness is higher. Again, a picture can tell 1,000 words, okay? So, is there a correct distribution, right? That's why you're here. You're trying to figure out, how do I know what is the correct distribution? The first thing you can start off with, is it data driven? Is there data that you could use behind it? If there is data that we could use behind it, then we're going to go ahead and do some distribution fitting to it. So if your data are representative of a population as a whole to your problem, you can most certainly use it. And again, we'll show you how to do that in just a bit. Is it theoretically correct? Okay, based on some implicit model of the input's behavior. So making sure there's potentially theory associated with it. Does it conform with industry standards? Ton of industry standards out there. If you are communicating with others and you say, oh, it's a Pearson 6, and they've never heard of Pearson 6 before, even if it is the best fit to your data, if it doesn't conform to your typical industry standards, you may get people questioning you as to why you used a Pearson 6 or Pearson 5 distribution, and then all of a sudden your entire analysis is under scrutiny because you chose something that is outside of these industry standards. So unless you have strong backing as to why, which you could show the distribution fitting, but then you're going to digress and just potentially confuse the people that you're discussing with. Is it pragmatic? Is there a pragmatic nature that we can actually step through and go through? Is it discrete or continuous? Is it bounded or unbounded? Is it symmetric or asymmetric? Are there, long tails or potential for long tails? So walking through those steps. And does it make sense? Does it make sense? So ideally, it would be a combination of all of these. And Everest does provide you with the capability of fitting your data. However, if you need to communicate it, just remember that you may want to be a little heavier handed on one or two of these than the others. Okay. So can you use your data? And I should stop and just see if there are any questions. So can you use your data for sales forecasts or projects? You're potentially going to have pre-existing data. So let's see if we can use that data, okay? So is your data that you do have representative of the population? And do you know the true bounds? And this is kind of one of those fun little things I kind of get excited about it. Like when you have subject matter experts and you say, what's the worst case scenario? What's the best case scenario? Like a common example that our consultants a lot of times use will be, how long does it take you to get to work? And then someone will say, oh, 20 minutes. And what's the longest it would take you to get to work? Oh, typically like 45 minutes or an hour. That would be a really bad day. That would be hitting lights and maybe some construction and everything. Is that the truly worst situation? Could there have been an accident? Could there be a major detour? Could there be 6 inches of snow? Like, there are all different bounds that could potentially happen on one side of that distribution. Now, certainly the longer it takes you to get to work is going to be the longer tail versus it taking you quote unquote less time, because based on speed limits and based on traffic patterns, there's probably a lot less chance. So it's going to have a distribution that represents a longer tail on the right-hand side versus on the left-hand side. So it will be asymmetric in nature. But knowing what those true bounds are, there is a left bound on that, because obviously it's going to take you some time to get to work, but it may not be the case for the right side, because there's going to be some bound, but what is that true bound? Okay. So where did your data come from is another important question to ask, okay? So let's hop into taking a look at some distribution fitting. And before I go into the full-on distribution fitting, I do just want to cover a few basic rules when we're talking about data. It's important to understand the difference between discrete and continuous, okay? A discrete distribution is going to be a situation where it takes on, the value drawn takes one of a set of identifiable values, so each of which has its own calculated probability of occurrence. So that Bernoulli function, where it was 0 or 1, there was a 30% chance of the 1 appearing. It's either 0 or 1. It's not 0.5, it's not 0.75, it's not 0.75555555. It's either a 0 or a 1. The Poisson distribution, it was either it did not happen. It happened one time, it happened 2 times, it happened 3 times, it happened 4 times, it happened 5 times, it happened 6 times. There is no, it happened 5.5 times. Okay, so it's either 0 or 1. Other things that you can think of are coin toss, outcome of a coin toss, outcome of rolling of dice, poker hands. There are only so many poker hands. Or if even drawing a random card from a deck of cards, there's only 52 different things. You can't have an ace and a half of hearts. You either have an ace or a 2 of hearts, okay? So that is a discrete function. A continuous function is going to be able to have an infinite number of values within a predefined range. Note that the range could be negative infinity to positive infinity. So in other words, we can only measure them to some degree of precision limited by our instrumentation, but they can have any value. So for example, asking someone to weigh themselves or the temperature, the speed of something. These are all situations where the instrument doing the measuring determines how precise that measurement is. So some examples might be, you know, stock price returns or allocation of wealth. So stock price returns would be log normal, and allocation of wealth would be Pareto. So that is one of the attributes that's important, really important to understand, because that's going to help you a lot when you're choosing your distribution. Next is going to be bounded or unbounded. I kind of touched on that a little bit talking about our duration of commute, but bounded is going to have set bounds on both ends, okay, which is going to be like your triangular distribution, which the parameters are, you know, minimum, most likely, maximum. That's going to have bounded. Your minimum and maximum are going to be bounded. Your PERT distribution is going to be bounded. Your uniform distribution is going to be bounded. Okay, it's not going to have those long tails on the end there. Unbounded is, it just goes on. Like there's complete potential for it to go on. It's unbounded. Now with unbounded, you might notice a little color pattern going on here. There's a method to my madness, I swear. The blue represents continuous distributions. The red represents discrete distributions. And I apologize for my squeaky voice. My squeaky voice is not healed, I don't think, since Nashville. But the red represents those discrete functions, okay? So if you notice, we have red with partially bounded, which would be the situation of the travel time, right? Because it's bounded on one end but not bounded on the other. And there's red in the bounded section, but unbounded, by its definition alone, discrete can't be part of unbounded, okay? So excellent. Thank you for the vote of confidence on my voice there. So yes, and if we think about an easy way, a lot of times I try to show people, like an easy way to think about this is when we think of discrete distributions, think it more of counting. It's counting. When we think of continuous distributions, think more of measurement. Okay? So I hope that helps a little bit to get those out of the way there. Now let's go into our example file here. And note that the example files that I'm going to use today, most of them are in the download that you already have, or your demo, or whatever it is that you have. But here we have a distribution fitting example. And this is an example where we have the demand of something. And I'll zoom in a little bit so you can see the values here. But we have a demand with the different weeks. And so we have this data. Now, if we want to just look at the data, we can go to Data Viewer here. And we can just say, I want to look at C2 to C158, just to see what that data looks like. So this is what the data looks like. So if this was our actual data, so for the gentleman who asked about, you know, what distribution should I use for sales forecasting? Well, if you already have some sales information, you could use that, or maybe you have previous information. So if you have previous data, you could map it out. But then what do you do with it? So that's what we're going to show you. We're going to show you that you can either fit a distribution to it, you can use your past data to come up with a pragmatic approach for it, you could use your past data and resample from that actual distribution, or we can use a distribution artist. For this part of the example, we're actually going to fit a distribution to it. And what does that mean? It means we're going to take this distribution, or this histogram, and we're going to try to find a curve that fits this. Okay, so how do you do that? Well, you simply go to distribution fitting here and say fit. And when we say fit here, we can then go in here to distribute, and this is a continuous sample data, so note that you're going to select the type. So in this situation, it's not a counted format, it's actually a continuous distribution. So we have continuous distribution. The distribution to fit is here. Now, I talked a little bit about the lower limit, like unbounded or bounded. We could say unsure to these, or because it's demand, we can say that it's a fixed bound of 0. And then when we toggle between unsure and fixed bound, you're going to notice that different suggested distributions appear. So you see how Cauchy is here? By definition, if it has a fixed bound of 0, that distribution will not be made available to us. Now, there are some people out there that can say, oh, well, in order to choose the accurate distribution to test, to see which is the best one, then you should choose a certain family of distributions and all this. For the level that you're at right now, what I would recommend is to simply say, select all. Let at risk choose which distributions fit best, and then you do the deduction and try to figure out which ones are industry standards, which ones are from families that your industry is familiar with. So we select them all, and then we choose fit. And now, if I scroll up on the left-hand side, you're going to see gamma. So the red curve here represents the gamma distribution that we would use with the parameters. What's beautiful about it is that at-risk figures out what those parameters are. So when we talk about distributions, you might have already noticed this when you're trying to choose your distributions and you open up and you're like, I don't know what the beta is. I don't know what the theta is. I don't know what the gamma is. I have no idea. I don't speak Greek. Then this actually provides those parameter values for you, okay? So here we have our distribution. I mentioned earlier Pearson 6. You know, this is what the Pearson 6 looks like. It's pretty darn close to the gamma. So either one of those would be representative, because the reality is we're just going to be drawing random values underneath this curve to represent those inputs. So you can go through and see which one you'd like best. Now, when going through this, note that by default, at-risk uses the key information criterion test, which favors fewer parameters, but so we have the AIC test here. There are also other tests that it does all at the same time. So you don't have to choose which test it does at the beginning, because it does all of them for you. And then you can go back and toggle between the different tests to see where the different distributions rank. But the other one that we have is the Bayesian information criterion. This also favors fewer parameters and is a better choice for smaller data sets. This is a pretty small data set, so maybe we should take a look and see what the BIC comes in at. Well, the BIC comes in at still with gamma on top. It still has gamma as the favored one. The next test that is available is a chi-squared statistic. This is the only one that can be used for discrete variables, and it's usually better when there are more than 50 observations. Then we have a Kolmogorov-Smirnov test, which is suitable for smaller samples, but has a better fit about the means versus the tails of the distribution. And the Anderson-Darling test, which is the last one, is more desirable when looking for a better fit at the extreme tails. So if we were in an industry that the information that occurred at the tails was more important than the information that occurred about the mean, then we're going to want to go with the tails. So we would do the Anderson-Darling test, and then all of a sudden you're going to see that the gamma drops down to the fourth choice as the best fit. You have a Burr 12 here. It's pretty similar, pretty close. We have the diagram, but then you're going to go back through and go, okay, would anyone know what a Burr 12 was or Pearson 6? They may not know, so you might just stick with your gamma. If you notice when I mouse over these values here, it will actually give the results of the 5 different tests for each one there, which is pretty cool. So you can actually see, even though it's at the top of the list, you can see, okay, if I mouse over gamma, it's number 1 for AIC, number 1 for BIC, number 4 for chi-squared and Anderson-Darling, and number 5 for Kolmogorov-Smirnov. So let's go ahead and choose gamma. When we choose gamma, we can just simply say write to cell. Then it'll say, where do you want to put this? I'll put it in this this particular spreadsheet for now, but I'll show you something in just a minute. So we can say OK. Now you're going to notice that that box automatically turned green. Why? Because if you've attended any of our other webinars, oftentimes I will have this color cells option on. What that means is it will highlight anything that is an input distribution in green, anything that's an output distribution in blue, and anything that has a statistic in, I think I have it in red or orange, I forget. So now if I go to define distributions here, this is our distribution that we could use to represent the demand in our other Excel models. So you can see here it has calculated the alpha and the beta, okay, and it has done those things. Now if I click OK here, if I want to just copy this and I want to go into a different spreadsheet, say I go to this one, just add a blank spreadsheet here. I can say here, and then just do demand. And you'll notice that here it says risk gamma. It has all of the same information I had. So even if I close out of that distribution fitting example model, I can still use this, and it is still going to be an input distribution. So if I go here, you're still going to see it as an input distribution, and that's what you would use for your input. Okay, so any questions about that so far? I'm also going to show you a batch fit as well. Okay, so we did our distribution fitting. Now let's take a look at what happens when we have multiple inputs that we want to fit at the same time. And for those that are used to modeling, we are well aware of the fact that we want to make sure that we take correlation into consideration. It's a pretty key ingredient to modeling correctly, because if we don't correlate our inputs and there is a relationship between those inputs, then essentially what we get as a result from our simulation is not going to portray what would actually happen. So we want to make sure we take into account those correlations. So here we have 4 variables, okay? Maybe these are stocks, maybe whatever it is, but this batch fitting tool is going to allow us to fit several contiguous columns of data simultaneously rather than doing each one at a time. And again, this helps because then it'll actually do that correlation. So similar to what we did before, we simply go to batch fit and we'll do a new one. And we'll see it's continuous sample data. We'll say distributions to fit. I'm unsure whether or not they're bounded or not bounded, so I'm just going to select them all. And I'm going to say go ahead and fit. And it'll go off and fit. It takes a little bit longer, obviously, because it's doing 4 variables. Okay, so here we have a situation where the risk triangular function is the best representation for that first variable. The risk fatigue function, fatigue life function, is the best representation of the second. Risk y-ball and risk Pareto for the other, Pareto 2 for the other ones. And it gives the actual parameters. Now, if we thought, oh, no one's going to really know what the risk fatigue life was, we can actually hop on over here to tab 2, and we can see across the top, we can actually see the different functions here. So if I go here, this is risk fatigue life, but we have inverse Gaussian, log normal, Pearson 5, Pearson 12, gamma, and I can go all the way through, and you can see them all at the top here too, but the one with the parameters is the one I was tabbing through there. And you can see where all of their rankings were. So you can see here all of their rankings are there. So these two were tied, log normal and log normal 2. So you can actually see the different parameters that were put in there, where they ranked with the test, their different P5s and P95s, so you can actually choose which one of these functions, and then you would just simply copy and paste this into your other spreadsheet. Along those lines, in the fit summary table, the report that's produced from doing this batch fitting, you will have a fit summary table. And you will see in the fit summary table the correlation between those different variables there. Okay, so then you can incorporate that correlation into your model as well. And I'm going to just take a quick peek. Okay, there was a question. Could you repeat the criteria of choosing the distribution based on tail versus middle? So that, I'm assuming you're talking about maybe when I was talking about the tests, the different tests that would be used, whether or not you would want to use the Kolmogorov-Smirnov or the Anderson-Darling. So if you were choosing if you wanted to choose the distribution based on things that happen about the mean versus those worst case scenarios. So if you think cost estimating, you might want things about the mean area and also include those worst case scenario, but we're not super, we don't, like if we're doing distributions to figure out whether or not we're going to bid on a project, we don't necessarily want to use a distribution that has the super tight fit on the tails. We would probably rather have some that has the super tight fit about the mean, because we don't want to overshoot what the potential costs are. So we're going to want to use a test that fits more about the mean. And so the Kolmogorov-Smirnov is about the mean and the Anderson-Darling is tighter on the tails. So I hope that helps clear that up. So what is the difference between distribution and batch fitting? The only difference is distribution fitting only fits one variable at a time. Batch fitting fits multiple. So it's basically like taking a bunch of individual distribution fittings and then also doing a batch fit to figure out the correlation between the individuals. Some of the other factors that we're going to talk about are going to be parametric or non-parametric. And I kind of touched on this a little bit when I was talking about the betas and thetas and gammas and alphas and all that good stuff. If I were to start my model from scratch and I went into a defined distribution window, when we go into our defined distribution window, we can see here we have a commons tab and we have a discrete tab. Those aren't too intimidating. Continuous gets a little more intimidating, but if I hop over here to the all tab, this is why we have so many people sign up for this webinar, because they look at this and they go, where do I begin? How do I know what I'm supposed to do? Where am I supposed to go with this? So this is what we're going to discuss right now. Okay, so let me hop here. We're going to start off with some key questions when we're trying to narrow down what we're going to choose out of that defined distribution window. We're going to answer some key questions about our data concerned. I mean, as far as choosing distribution is concerned. So the first question we're going to ask is it continuous or discrete? So is the variable we're trying to represent continuous or discrete? Is it symmetric or asymmetric? Does it have a long tail or on either end? Is it bounded or unbounded? Is it parametric or non-parametric? Does it represent a population or does it represent just your sample size? And what are those extreme values? What are those black swan situations? I did a webinar once before that was, someone had said, why wouldn't I just use a normal distribution and truncate off the tails? And it's those tails a lot of times that's going to have the risk in it, right? So that's what we're going to want to be prepared for in some situations. I assure you that the people down in Houston would be really bummed to find out that maybe somewhere along the line they modeled that there was going to be this crazy hurricane that blew through there and they were on this tail, but someone just decided to truncate it off. You know, so we want to be able to be prepared. So those are some of those key questions that we want to be able to ask ourselves. So how do we do that? I have this fun little, I'm going to cancel out of here and I'm going to close this up because I have a fun, actually, before I close this up, I will also show you, if you're in industry, there are sometimes some key ones. I have slides at the end that will go through these, but know that this will be in your files that I will send to you. But occasionally in finance, you'll have the normal distribution, and that'll represent for change in price from one period to another. I just noticed I have a typo there. So Poisson would be the number of events, crashes, earthquakes, that sort of thing. So note that this will also be in there, but it's part of your tab right there called industry. But I'm going to close that out and show you another file that I put together. called Choose the Distribution Flowchart. And I did not create this myself. It actually was derived from D. Aswath's Strategic Risk Taking, a Framework for Risk Management. I actually pulled this chart out of his book and just recreated it using our other product called Big Picture so that we could give you a tool that can be used to walk through your choosing of your distribution. Okay, is it discrete or continuous? If it's discrete, can you estimate the outcomes of the probabilities? If yes, then you would use this discrete distribution. If, you know, if they were symmetric or asymmetric, you'll have symmetric and asymmetric. Are the values clustered around the central value? If so, then you would use a binomial or discrete uniform. If they're skewed, how are they skewed? Is it a strong positive skew, moderate positive skew, negatively skewed? And you can walk through this. So for those people that were wondering, oh, can I only do it if I have data before? You can also do it this way. This is the pragmatic approach, taking one step at a time, going through it. So not only do we have it for the discrete, we also have it for the continuous variables as well that we'll go through and suggest to you. Is it the end-all be-all? No. Does it include all of our different functions that are available in our defined distributions thing? No. What it does include is it includes the most popular ones. So that's where we want to take you with that, okay? So just know that that's also that possibility that you can kind of walk through everything and figure out on your own which one you would use. So another situation that we can talk about are those industry standards. I mentioned those earlier, so let me just quickly hop over here and talk about some of those industry standards, and I am going to show you how to add some distributions in Excel. I just want to cover some of these other basics as well. But industry standards in finance and insurance, normal could be used for change in price from one period to the next for short periods, and log normal for longer periods. Poisson is the number of events, crashes and earthquakes. Pareto or log normal is severity and magnitude. Oil and gas. There was a couple of questions I saw pop up that were related to oil and gas. So these are going to be some of the popular ones in your industry. Project management, I did have someone else from project management in here. Triangular is super popular, and I'm going to show you the difference between a triangular and PERT distribution when we get into our next example file. But cost estimation and schedule risk when it is a new project. Keyword is when it's a new project. If it's a project that has been around, or so you could do the PERT distribution, which is cost estimation and schedule risk when there are experts involved or previous data. So to go by, and I'll explain why in just a second. Binomial and Bernoulli, we already discussed this. Will a particular event happen or not? And then also in nature, having the log normal possibility as well. There are two files that I really want to walk through with you. I want to show you the example of when we used Bernoulli function. So this is a situation of essentially calculating out a 10-year net present value with a known input of a discount rate of 10%, initial investment of $1 million. We do have some uncertain inputs, and it's those uncertain inputs which is where we're going to see and have the different distributions representing what we have. So here we have the Bernoulli function representing the competitor entering the field or not. So we have this 10% chance that a competitor is going to enter, and the reason why it's 10%, we can see here that the probability is located in cell E8. If I look, we can see cell E8 has 10% in it. So there's a 10% chance that this will be a 1, and then if we click off of here and take a look at sales volume, we're going to see where that 1 comes into play. If cell C8 equals 1, then we want to use C11. If cell C8 does not equal 1, then we want to use C12. How would I know that this is where it was? Because Lord knows that our spreadsheet models can be a lot bigger than this. This is a pretty small one. That's where I say you want to take advantage of the fact that we are in at risk. So, we are in Excel. So when we look at this, we can say where our trace precedence. What's linking to this? Okay, these are the 3 cells that are linking to this one. So, or then after that, where does it go? We have trace dependence on this as well to find out where these values are going to affect our model. Okay, so take advantage of the fact that you're in Excel and really understand that model logic. And the model logic is basically, heck, if there's a competitor, then there's going to be less money made. There's going to be less sales volume because there's a competitor. If there's no competitor, then our sales volume will be higher. And in this situation, maybe we had experts come back and say normal here. It's not something that a lot of financial people would do, but maybe they represent it with normal and their standard deviation. So they've maybe done some subject matter experts here, and then they decided on triangular distributions for the rest of these inputs here. That could be certainly the case. So what happens when we run our simulation? Let's just do 1,000 simulations here. So if we do 1,000 iterations for this one simulation, I want to put this in demo mode. So I want you to just take a look at how the competitor one is going to change. We can go start, and it'll be taking different values throughout. So you can see that every once in a while you're going to see a 1 pop up there. And if I wanted to go through it step by step to show you, I could also choose to hit my F9 key. And when I get to a 1, at some point when I get to a 1, there we go. When I get to a 1 here, you're going to see that this sales volume is pulling from here, which then will affect our output. And in this case, our output is net present value total. So we can look at this and say, okay, over a 10-year period, what's the chance that we'll make $250,000? There's only there's a 95% chance that we will exceed a million. I'm sorry, there's a 4% chance that we will make less than $250,000. Okay, so now we can actually utilize our output in this situation. So another example that I want to show you is when we have a situation that has a risk register in it. Actually, I will open up one here. Okay, so let's zoom in on this. If it lets me here, let me zoom in. Okay, so we have a situation here where we have, and this is where I'm going to show you the difference between PERT and triangular. So in this example model, this is a cost estimated model. We have this risk triangular function chosen here. If I go to define distributions on this, we're going to see we have a minimum, most likely, and max. And those are pulled from cell G3, H3, and I3. So that's these values right here. Now, if I look at the values that are the percentages that these values are based on, we're going to see that we've kind of already built in this heavier on the tail for costs, because we can see that, raw materials, there's only a 5% differential between minimum, most likely, and then maximum has a 25% differential. So we've kind of already built in that heavier, may cost more factor. And when we're doing cost estimating, yes, it's important to have maybe a little heavier on what we think it may cost so that we're better prepared than caught with a short bank account, right? So how do we know whether or not we should use triangular or PERT? Well, one of the beautiful features is this add overlay. If I take the add overlay and I overlay a PERT distribution on this, okay, so I overlay a PERT distribution and it automatically is pulling in the same values that we had for the triangular, we can see that if we were to look at this, let me drag this out a little bit here, if we were to look at this, when we're drawing random values from this, whatever distribution we choose, whether we choose the PERT or the triangular, you're going to see that it's going to draw more values that are worst case scenario, super heavy costs, super high costs. we've already taken into account that we wanted a little on the conservative side, shall we say, by doing this higher percentage for the max. So in this situation, we might be better off using a PERT distribution, because maybe this is a project that we've already done before, and maybe that's the PERT will be more about the mean, and the triangular is going to be a little heavier on the tails in a lot of cases. Now, you might have seen when we did, when I showed you the industry slides, that it said, you know, if it's triangular, use triangular when it's a brand new project. If this is a brand new project that is unlike anything else that you've ever done, you don't know where the true mean is, or I mean the true most likely is. You don't know where that true most likely is. And if you don't know where that true most likely is, there's no sense centering around it because you've never experienced it. So in that case, triangular distribution would be okay. So that's just a little tidbit of extra knowledge for that. And then down here we can talk about some risk registers. Risk registers are those situations that, if you're not familiar, risk registers is like those things that could happen. They're more than likely not going to happen, but they could happen. And if they happen, they're going to affect our costs in some way. So how do we represent this with functions, distribution functions? Well, a worker strike and an earthquake, that'll probably only happen one time, right? One would hope it would only happen one time. So we will model that with the Bernoulli, which is that on-off switch, 0-1 switch. However, bad weather could happen more than once. So what does that look like? If there's a 60% chance of bad weather, we're going to use the Poisson distribution to represent the 60% chance of bad weather, which would break down to this. So we can see that for 1% of the time, it's going to be about 33% of the time it'll happen once, okay? And for about 10% of the time it'll happen twice. And then for about 2% of the time it'll happen 3 times. And then if I go here and drag my delimiters over here, and all I'm doing is surrounding the discrete bar represented here, we can say about 55% of the time it won't happen at all, okay? But the rest of it is factored in here, okay? So when we look, and if I turn on my dice icon, I want to get to a point where instead of just a 1, I want to see a 2 or a 3. So just, there we go. Oh, that happened nice and quick. Thank you. So we have a 2 or a 3. That represents the number of times that we have bad weather. And in risk registers, you're typically going to have the frequency of occurrence and then the severity. So the severity in this case is being drawn from a PERT distribution. We can see in this formula up here. It's being drawn from a PERT distribution. A PERT distribution using the minimum, most likely, and max that is shown here. And that's coming up with $959,000. Now, this is all well and good if it happens just once. The key thing that I want to make sure that I point out is if this were to happen twice, what are the odds that both times it would cost exactly $959,000 in increased costs because of bad weather? It's probably unlikely. So in this case, instead of doing a risk make input of comparing these, basically multiplying these two out and doing a risk make input of it, it may be in our best interest to use what's called a risk compound. The risk compound does slow down your spreadsheet a little bit, so if you do have an extensive spreadsheet, then the risk make input might be a better situation. But in general, when you have these multiple chances of occurrence, better to use risk compound than risk make input. If it's a single chance of occurrence, then go ahead and use risk make input. But for this one, risk compound, what it's going to do, you can see here, the structure of it is risk compound. It takes the distribution in D8 and the distribution in D18 and the distribution in H18 and draws randomly at the same time, which is pretty beautiful, because then we have a situation that when there are multiple events that happen, let me see if I can get back to it too. That might not happen quite as, oh, I just skipped by it. But anyway, it will actually pull up a different value here than just multiplying by 2. So I hope that helps a little bit there. I'm going to take a quick peek at questions, and then from there we can do one more example file and then we'll wrap it up. If I have historical data but no best fit with availability, with no best fit with available distributions, can I use the artist to input my data as a distribution? I love this. Did you already watch this webinar once? That is exactly where I'm going to next. In the infamous Old Faithful data set, which so many people probably remember from their Stats 101 days. So let's go ahead and open that so we can explain to people exactly what you're talking about. And yes, the answer is absolutely, highly encouraged. Okay, so Old Faithful, the infamous Old Faithful data set. If we take a look at waiting times, and I actually already created the histogram just to make it a little bit faster for us here, but if we had taken a look at our waiting times of Old Faithful eruptions, you will see that it's actually a bimodal distribution. Okay, so say I had gone here and I took a look at my data viewer and I said I want to see what C1 through C, oops, not C11, C1 through C273 looks like. It would look like this, right? And these are the different waiting times in between. Now, I could try to fit a distribution to this. If I try to fit a distribution to this, let's just see what comes up. Whoa, right? Whoa. Does that fit well? Does that represent what could happen? Look at how many values will be drawn in between here that didn't exist in our original data set. What about a triangular distribution? Could that fit? And let me zoom in here a little bit for you. Is that a good fit? No. I can't even pronounce this one. Kumaramaswamy. That doesn't fit well either. So none of these fit. So what do we do? Are we stuck? How do we represent this? How do we create a simulation using this input if we can't even get a fit distribution off our existing data? Well, if I were to put this into a histogram like you see here, I can use what's called our artist. This is our distribution artist. And we can say that in this case, let's go. Wait times, and we're going to do a histogram, and we're going to say the minimum is 40 and the maximum is 100, and the number of bars in that graph that we have from Excel is 8. So we're going to say okay. And now to create this histogram, the first thing you do is just click anywhere in the graph. So if I click, it creates this default histogram. Then if I go over here, I can mouse over and go, okay, that's 26, this is 40, this is 28. So then I can go to my artist and I can drag this up to 26 and 40. I'm not getting an exact, but close enough, and 28. And then I can go here and say 19, 67, 69. So we can go back here and do 19, 67, 69, and 22, which is pretty much where it's at. 22, and this is pretty much at 0 here. 1. So now all of a sudden I have this distribution that I could use. So I can say right to cell, and I can say I want to put that right here, and we click OK. Now if I go to define distributions, it's going to pop up and have this distribution. So when at-risk goes through and does a simulation, it will draw a random value underneath this distribution, which very closely resembles what we had in the past. So we can actually draw a random sample underneath here. Another way that you can go about doing it is what's called risk resample. We're going to do equals risk resample. Okay, and if we do equals risk resample and click on the function tab, you're going to see here, okay, what is the sampling method? We get to choose whether or not we're going to do it in order, which in this situation you wouldn't, because obviously if we're going to try to simulate what could happen in the future, it's not going to happen in the same exact order that all of these happen. However, that may be a situation where maybe you're assigning numbers to certain students and they have to go in a particular order, then that would be a situation where you could go ahead and use the number 1 sampling method. The number 2 sampling method would be random with replacement. And this would be a situation that would be appropriate for this, because we can go ahead and plug in random with replacement, and then it will draw values out of all of these values in the set and then put that value back in, and then possibly it could be drawn again. So in this situation we could say 2 for sampling method, and then we can actually go here and say out of these values here. So control shift down gets our C2 to C273. Okay, so now you're going to see if I click my F9 key here, you're going to see it's going to draw values here in the green. It's drawing random values out of these values that were in those 272 cells. And then all of a sudden when you run a simulation that has 1,000 iterations, granted I don't have an output for this, but you can still quote unquote simulate it. You see it'll actually, so the red is doing what I drew, okay, and the blue that's hiding behind it is what the original was. So it's pretty close, but it's not exact. So if I were to zoom in here, you're going to see there are some situations where we drew a couple more reds than what were in the original data set, but that would be super close. So risk resample is also another option that you could use. And with that being said, let's hop back to the slideshow here and just discuss a few more things. Other items to consider is theory. Theory is, you know, does it make sense in what has happened, and theoretically what has happened in the past, and that's something we'd want to take a look at. Calculated statistics, maybe you have calculated statistics from a subject matter expert on your particular sample size. Previous experience, huge, okay? What are the chances of this happening again? What are some of the situations we're going to have? Expert opinions, of course. Expert opinions are super important, and expert opinions are important throughout the whole process, really. And the key, though, is with expert opinions is to not be afraid to also challenge them, because they may not understand this. Challenge them when they're talking about bounds in worst case and best case scenarios. Challenge them a little bit to really see the bigger picture. And then also sensitivity analysis. If you have a model that has thousands of inputs, are you going to want to go through this process for every single input trying to figure out what is the best distribution? No, you're not going to want to do that. What you could do at that point is open up top rank, choose your output, auto vary inputs, do a what if analysis, see what your key inputs are, and then only focus on choosing the most correct distribution or the least wonky distribution for those key drivers that are your key inputs that drive that output. Final thoughts. Let's just go there. Choosing the right distribution is important, okay? But don't panic, because there is no perfect distribution. Okay, there are no perfect distributions. That is, if you think of the whole concept of Monte Carlo simulation, it's not like there's this magic 8-ball that's going to tell you exactly what's going to happen. It truly is a situation that there's going to be variability in it. So even if you don't have the exact perfect distribution, know that the distribution that you have, as long as you've used some common sense, is going to be better than no distribution at all. When we talked about sensitivity analysis in one of them, there was a consultant that used to recommend putting uniform distribution in for all of your inputs and run a simulation, do a sensitivity analysis, and then go back through and find out, fine-tune which distributions you would want to adjust based on which inputs had the most impact on your output. So just use that common sense. Think about who you are sharing this with. If this is for your own personal business, that's a different story. But if it's for a CEO or a major decision maker or a major corporation or a board or whatever it is, think about who you're sharing this with, because that is going to be super important. Just know that it's not going to be perfect, but whatever you choose, the fact that you're using simulation is way more informative and a way better approach to making really important decisions. So I really hope that this has absolutely helped out in understanding and just giving you a better guideline on which distribution you should choose. It really is an individual process. It's not a global process. We can't just say in every situation representing times of flight, we always use this distribution. It's going to depend on where are those flights coming out of, where are they going to, what about, is it later in the day, is it early in the day? So there are going to be different variables that are going to impact that. So I really hope that this presentation was helpful to you. I appreciate each and every one of you coming out, and if you have any questions, feel free to reach out to me. I can't do consulting services. That's not my forte, but I can most certainly hook you up with those people that can. And I just want to say thank you. Thank you for taking the time out of your day to join me. And I really hope you have a fantastic holiday if you're here in the United States. And otherwise, to everybody, I bid you adieu and hope you have a fantastic week. And thank you for joining me. Bye for now.